Welcome back to Lecture 3. This is the part of the lecture on equilibrium constants. This is actually a chapter quite a bit removed from some of the other stuff that we've done numerically, but it does follow right in line with rate constants with kinetics, and so that's why we have it so early in the course. But I think you'll find it joins in really well with our previous discussions. So if we look at equilibrium, all of our reactions that we've written so far have occurred just in one direction. We've shown a single arrow for our when we write our chemical reaction. We show it going from reactants to products. And as it turns out, very few reactions occur in only that one direction. We've seen that we have collisions between reactants turn into products. We haven't really asked ourselves what happens if products collide. Well, we can get a reaction between products as well, and they can actually recreate reactants. And so you have reactants colliding to create products, and then you have something that's called a reverse reaction, where you have products colliding and giving us reactants back into the reaction vessel. So as the reaction proceeds in the forward direction, what happens? Well, we start with all of the reactant molecules that we possibly have, and as those reactant molecules collide, they start to create products. Well, this means that we have fewer reactant molecules present because those reactant molecules have been turned into products. So as a result, the concentration of reactant molecules goes down, and as we learned, as concentration goes down, reaction rate slows down. So as a reaction proceeds in the forward direction, that forward reaction rate slows down. The rate of turning reactants into product decreases. But what happens in the reverse? Well, as we start to create product from reactant, we are gaining more product molecules. And so the concentration of product is increasing. As the concentration of product increases, the number of collisions between product molecules increases, and this means that the reverse reaction rate increases. So in the forward direction, we have a decreasing reaction rate, and in the reverse reaction, we have an increasing reaction rate. At some point, those two rates are going to be equal, and once they're equal, the rates stop to change, and we call that a state of dynamic equilibrium. Now, the reaction appears to have stopped. If you're doing some sort of analysis where you're checking the concentrations, you'll find that the concentrations stop changing after some point in time, and that's that state of dynamic equilibrium. So it looks like the reactant molecules and the product molecules all looked around and said, hey, we're all equal, we can just stop. But they don't stop because they still have thermal energy, they're still moving, they're still reacting. The only thing that stopped changing is the concentrations. But the reactions themselves are still taking place. You still have products turning into reactants, reactants turning into products. The only difference is now they're happening at the exact same rate. So it looks like nothing is happening, but it's still a very violent place inside our chemical reaction. Now, at equilibrium, one of the things we have to be very careful of is that term equilibrium. The only things that are equal at equilibrium are the forward and the reverse rates, and that's it. A lot of people have a misconception that at equilibrium, the concentration of products and reactants are equal, and that is just simply not true. It can be true, but it doesn't have to be true. Sometimes we reach an equilibrium with a tiny bit of reactant left and lots of product, or sometimes it reaches equilibrium in the opposite direction. Sometimes we have lots of reactant left over at equilibrium and only a small amount of product made. So it can really go anywhere in between those two extremes. Now, when a reaction has reached equilibrium, we indicate that type of reaction with a forward and reverse arrow. And you see that right there. And when you see that double arrow for a reaction, it means that that reaction reaches a state of equilibrium, and at that state of equilibrium we can say that rate in the forward direction, that's that little 4, is equal to the rate in the reverse direction. Now, if we go back to what we just did with kinetics, we know that we can write the rate for the forward direction here for A turning into C as K forward, so the rate constant for the forward direction, times the concentration of A. is equal to the K for the reverse reaction times the concentration of C. Okay, so we know those two things are equal because the rates are equal. So all we're going to do now is just rearrange our equation. We're going to bring our K reverse over here. We're going to bring our concentration of A over here. And so what we end up with is we have our rate constants grouped together, and we have a rate constant over a rate constant. So we have a constant over a constant. If you have a constant divided by a constant, that's going to be another constant. And the key with these equilibrium, or with these concentrations right here, our concentration of C and A, these are equilibrium concentrations that have to be used here. You cannot use initial concentrations there. They have to be what the concentrations are when the reaction has reached a state of equilibrium. Now, since we have a constant over a constant for those two rate constants, we call that a whole new constant, and notice that we use a capital K, and we call that an equilibrium constant. There are several different kinds of equilibrium constants. They are all given a capital letter K, like we see there. The little EQ there just means that this is a constant of equilibrium. There's lots of different things that we put in place of that EQ. There's lots of special types of equilibrium constants. We'll explore some of those a little bit later in the course. There are many more that we won't explore in this course that you may come upon in later chemistry courses. But we have our concentration of C over concentration of A here. Now let's expand our reaction a little bit, and let's get a bigger reaction, a more generic reaction. So we have AA plus BB goes to CC plus DD. Just like we had for our kinetics example, the capital letters are our reactants and products, and our lowercase letters are our stoichiometric coefficients. Now, what we couldn't do with our rate laws, we can do with our equilibrium constant expressions. We can use the stoichiometry of the reaction in order to write our equilibrium constant expression. And what we do is we put the concentrations of the products divided by the concentrations of the reactants, and we raise each of our reactants or products to the power of the balancing coefficient. So what we have here is we have our products on top, concentration of C, concentration of D, and notice that the concentration of C is raised to the little c. That comes directly from a balancing coefficient. Same with D, same with B, same with A. So in order to write an equilibrium constant expression, you first have to have a balanced reaction. If you haven't balanced a reaction, you cannot write a proper equilibrium constant expression. So for this reaction here, H2 plus I2 goes to 2HI. We have an equilibrium constant that's equal to concentration of HI squared divided by concentration of I2 times concentration of H2. Okay, that 2, didn't want to point this out here, so the 2 that comes right here is a result of that 2 right there. The I2 and the H2 have no exponents there because their coefficients are 1. And here's another interesting thing about our equilibrium constant. The equilibrium constant has to be met when the reaction reaches equilibrium. That means that those concentrations at equilibrium of the reactants and products, no matter what they are, have to meet the ratio given by the equilibrium constant. So this is really, I find, a fascinating table. So what we've done is we've taken 5 different experiments here, starting with different initial concentrations. So here we start with 0.5 and 0.5 and no product. Here we start with no reactant and only product. Here we start with equal amounts of reactant and product, double amount of reactant, 1 reactant and no product, and vice versa. And notice that we have different amounts of reactant and product left at equilibrium for all of those different situations. However, when you put the concentrations of what we have at equilibrium into the equilibrium constant expressions, notice that every single one of them ends up with a value of 50. Okay, so that's the equilibrium constant for that particular reaction at that particular temperature, and that means that no matter what the starting conditions are, You have to have that ratio of the concentration of HI squared divided by concentration H2 times concentration of I2. That ratio has to equal to 50 at equilibrium. It also tells you if you're at equilibrium or not. If you don't have a value of 50 for those ratios, then your reaction is not at equilibrium. So what can that value of equilibrium, of the equilibrium constant tell us? Okay, because equilibrium constants have a vast array of values. They can go from extremely small values, 10 to the minus 20s, 10 to the minus 30s, to extremely large value. We see one there on the screen at 10 to the minus 12. They can go higher than that. They can go 10 to the minus 40s, 10 to the minus 50s. They can be just huge. So just an enormous range of equilibrium constants. So what does that value tell us? Well, if the K is a lot larger than 1, and when we say larger than 1, we're thinking like greater than 1,000. So it has to be greater than 1,000. What that means is that at equilibrium, we have a lot more product than reactant left over. A large number means that we have a high numerator and a low denominator. That means we have a lot of product and only a little bit of reactant left over. What we say for a reaction like that is that the reaction favors the products. It would prefer to be on the products side. If products are what you're trying to make, that's a good thing to have. If you have a K that's much smaller than 1, now when we say much smaller than 1, what we mean is generally less than 1/1000th, 10 to the minus 3, smaller than that. So what that means is that at equilibrium, you have still most of your reactants left over and only a very small amount of product has been formed. For these types of reactions, we say that the reaction favors the reactants. Okay? It means that this reaction really does not like to happen. And then if you have a K around 1, and that's a little bit of a weird term, around 1, because normally if you say something's around 1, you're thinking like 2 or 3. Well, no, it can go anywhere from 1/1000th up to about 1,000. So that's actually a fairly wide range as well. Different people have different things. This is just something I was taught long ago, and I've stuck to that, and I've seen other books use that same range, so I think it works out fairly well. So if it's between 1/1000th and 1,000, what that really means is that the products nor the reactants are heavily favored. It means that at equilibrium, you're going to have a lot of reactant and a lot of product left over both. These can sometimes be the worst type of reactions if you are trying to isolate one of your products, because if you're trying to isolate one of your products, it means you've got to try to get all of the reactant out of there as well. And that can be somewhat difficult depending on what phase everything is in. But anyways, those are the different values that we have for our equilibrium constant. Now, I mentioned earlier, if you were to check your reaction and you find a value is not equal to the equilibrium constant, or you put in your concentrations, you do a calculation, you find it's not equal to the equilibrium constant. That means that your equilibrium is not, or your reaction is not at equilibrium. So to look at that, we have something called the reaction quotient, or QC, sometimes just Q. The Q is really the same as the K. The C just means that we're using the concentrations in the calculation. So we have a little Kc right there, and all that means is that's the equilibrium constant calculated with concentrations. So when you do a K calculation for equilibrium, you are assuming that the reaction is at equilibrium. When you do a Q calculation, the calculation is exactly the same. The only difference is you are not assuming that the reaction is at equilibrium. So we use Q to determine if a reaction is at equilibrium or isn't it. As far as the calculation, like I said, it's exactly the same as the equilibrium constant calculation. The only difference is what your assumption is. So we use the value of Q to determine if a reaction is at equilibrium, and we can also use it to determine which direction does the reaction still need to proceed in order to get to equilibrium. It depends on where you're coming from with your reactants and products. So let's go back to our H2 and I2 reaction. So we see that it makes 2HI. We've written an equilibrium constant for that one before, and so our equilibrium constant written in terms of concentrations. We could also have put an EQ there. It's no different. We have concentration of HI squared over concentration of H2, concentration of I2. When we do an equilibrium constant calculation with these concentrations, we are assuming that these concentrations are equilibrium concentrations. If they're not equilibrium concentrations, then we cannot calculate a proper value of K. So, in order to check to see if it's at equilibrium, we calculate a Q. Notice that it's the exact same formula, concentration of HI squared over concentration of H2 times concentration of I2. These are concentrations taken at any time t during the reaction. And really, if you don't know if a reaction's at equilibrium or not, then you're calculating a Q. If you know it's at equilibrium, then you're calculating a K. That's the only difference, is what do you know and what don't you know for these reactions. The calculation is exactly the same, just how you use them is different. So let's compare these two values, K and Q. A K value for a particular reaction, oftentimes you can look up in a table, in a book somewhere, because it's a constant. Somebody will have done that reaction under the same conditions you are, and those equilibrium constants are published, and they will always be the same as long as the conditions are the same. Qs aren't like that. Okay, so that's why you always have to calculate a Q. You can usually look up Ks. So if you are doing a reaction, you don't know if it's at equilibrium. You take out your sample, you measure concentrations, you do a quick calculation. If you find that the Q value that you just calculated is greater than the K value, what it should be, what that means is you've got more products than you have reactants at equilibrium. Okay, that means that you have too much product and not enough reactant to be at equilibrium. And that means that the reaction still has to move in the reverse direction. You have to consume some product to make the concentration go down and create a little bit more reactant in that reaction in order to get to the equilibrium concentrations so that the ratio will be equal to K. Vice versa, if Q is less than K, that means that the reactants are more abundant than they should be at equilibrium, and that means that the reaction is still moving in the forward direction. You're still moving from reactants to products. The reaction needs to shift to the right, towards the product side. I guess that this would be my right. Towards the product side in order to reach equilibrium. And then if you do a Q calculation and you find the value is equal to K, well, now you can say that the reaction is at equilibrium. You know where the reaction is. It does not have to shift anywhere to get to equilibrium. And so what you've actually done in that case is a K calculation. I know that sounds confusing. Let's take a look at an example. So we have H2 plus I2 goes to 2HI. It has an equilibrium constant of 54.3. Where did I find that? I looked it up. I went to a table and I looked up what is the equilibrium value of this particular reaction at a particular temperature, and it's 54.3. So I do a reaction and I pull out a sample at some point during the reaction. I don't know if it's at equilibrium or not, but I want to know if it's at equilibrium. So when I analyze the sample that I took out, I find I have a concentration of H2 at 0.243, I2 is 0.146, and HI is 1.98 molar. So is the reaction at equilibrium? Okay, I have to do a Q calculation. If it's not at equilibrium, which way does it need to shift? So again, my Q calculation is the exact same as my K. I have products over reactants. I have my coefficient of 2, my exponent of 2 from the coefficient of 2. So we write that expression the exact same way. So I plug in my values. HI is 1.98. My H2 is 0.243. My I2 is 0.146. When I calculate that, I get a value of 111. So what does that tell us? We see that the Q is greater than the K. If Q is too big, that means I have too much product and not enough reactant. That means that my reaction will still be moving in the reverse direction. That probably means that I started with just HI, or maybe I had a mixture of H2, I2, and HI, and I had more HI than needed to be at equilibrium. So this reaction will proceed to the left. Some of this material is a little bit to absorb mentally. It's one of those things, if you try to grab onto it too tight, it's like trying to grab jello. It's just going to squeeze through your fingers. Just kind of hold it gently in your head, let it sift around a little bit, and think about it. So Q and K, basically the same thing. The only difference is K is for one very specific point during the course of a reaction right at equilibrium. Q is everywhere else. If you have any questions on this material, make sure you contact me. Good luck.